Okay, so what we're going to do is go through an example, a very simple example of conservation of control volume analysis. And our first example is going to be finding the force on an elbow in a pipe flow. So what happens here is you have, for example, one pipe, and at some point in that pipe you hit an elbow. Let me try to draw a little clearer. So we have a flow in a pipe, and you hit an elbow, and it turns the flow down, and it necks down to a smaller pipe. So what we're asking is, what is the force on the elbow? So one of the first things you'll do is start off with some givens to the problem. And we're going to have the givens at a few different points. We're going to call this point 1 and this point 3. At point 1, we're given a, let's say we're given a mean velocity, pressure, and area. At point 3, we're given a pressure at point 3, and area at point 3, but velocity of 3 is unknown. Another thing that's going to be given in the problem is a density. So the next thing we want to do is come up with some reasonable assumptions. Right? What we're going to do is call it compressible, density is constant, and we're going to say that this is a steady flow, which is it's consistent with a flow through a pipe. So in a control volume analysis, a key part of it is defining the control volume. And here I'm going to define it right inside the pipe. That's going to be phase 1. Phase 2 is going to be right inside the elbow and go all the way around. And phase 3 is going to be, so that's phase 3. It's going to be the outlet of the elbow. And phase 2 is going to be this control surface that matches or butts up to the edge of the wall and inside the pipe. So here is our control volume. And I'm going to... So the next thing we want to do is start looking at our unknowns. We defined our control volume, and I'll just make a few notes about this. So our control volume has, how are we going to get to our force on our elbow? We're going to use momentum theorem. That's conservation of momentum gives us forces. And what we need are the forces on surface 2 to get the elbows. But what it demands is understanding things like the momentum flux into the system and the momentum flux out. We do not know momentum flux out, so this tells us we need to apply conservation of mass first. The goal is to find V3. From our notes, what we're looking at is conservation of mass can be defined as time rate of change of density or of mass in the system plus the momentum flux out of the system equals 0. We said that this is steady, so this term becomes 0. And what we want to do is divide this, apply to control surface 1 through 3. We have control surface 1. Control surface 2. Just breaking up that integral into 3 different integrals. And control surface 3 equals 0. So this is our conservation of mass in the steady limit where we've broken up into each individual control surfaces. So then we want to start evaluating these integrals. So key thing is this dot product from the velocity vector. Okay. So in the context of this ds, remember, ds always points out. So that points out there and it points out there. So if we first come to this first one, what we have is a scenario where ds points this way, velocity vector points this way. So this term, the sign associated with this term is going to be negative. With that in mind, our integral becomes rho times negative, less negative sign, velocity at 1, area at 1. This ends up being our integral because it's a constant all the way through. Constant velocity at 1 and 3. So we're assuming that this is a constant profile. So if we go to the second term, what happens here? So in general, if we look at our control surface on our elbow, ds is going to be there and there. And our velocity vector is always going to be perpendicular. So this implies 0. This entire term is going to be 0. So the third term is somewhat similar. We have our outlet. It has a ds this way and a velocity vector this way. Because of that, we have a positive sign. So this third term is rho v2, no, v3 a3 equals 0. So if we look through this, we know we were able to solve for v3 equals v1 a1 on so that handles one part of the problem. So the part 2, we want to find or apply conservation of momentum. And this gives us find what we're force on our elbow, what we're ultimately after. So we do essentially the same thing. We apply the same control volume, but instead we apply the conservation of momentum, which is given as the time rate of change of momentum in the control volume plus the momentum flux out of the control volume, which is going to be equal to pressure force on the control volume. So essentially the integrated pressure actually acting on the control surface plus the shear forces fluid acting on the control surface. So in general, this is similar to before. And these are surface forces. So what we're going to do is break this up into two sides. Left-hand side and the right-hand side. Let's start with the left-hand side. So volume term, so our momentum inside the volume, plus this thing's going to expand, this term's going to expand to three different terms. So we have surface 1, the momentum flux, momentum flux out of the control volume on surface 2, and the momentum flux on the control surface 3. This one is 0, steady, because we have a steady flow. From before, this has a negative sign. This is a value of 0, and this is a positive value. This first term ends up being rho times V1. From here, we have a vector because it's in the x direction. So I'm going to give it a vector unit of I times negative V1 A1. That's this dot product with this negative sign. We have 0 in this term, so we have no momentum flux going out of the walls. The walls do not enable penetration. Then we have this third term, which is rho V2 in the j direction. So we have this, and then we have a negative, actually it's a positive V2 A2. But before, recall, we found that, sorry, this is not V2, this is V3. 3 was the value in the outlet. So then we'd already defined V3 in terms of V1. This was V2. This is V1 A1 on A3, and that is V1 A1 on A3. Simplify this to get rho times V1 squared times, so it is negative A1 in the I direction from this and this, and then we have positive A1 sorry, this was A3, A1 squared on A3 in the j direction. So this gives us the momentum flux out of the system, which is what this left-hand side gives us. The next thing we have to deal with is this right-hand side. So the right-hand side, recall, it's the surface pressure and the shear stress. So we go back up to our control volume. Remember, we have a pressure here, and it's applying a force to the control volume. And as well here. So we have this negative surface force on 1 of pressure times ds. minus the force 2 minus the force on surface 3. And we also have shear force on the fluid, surface 1, plus shear force on the fluid on surface 2, plus shear force on surface 3. So let's talk about these a little bit. So this term and this term are going to be, again, the pressure force acting on each side of the control volume. So again, P1A1 is going to be that. Down here, we have P3A3. It's going to be this term. You could see that the sign, remember, this ds is out, is outward, so this negative sign puts it in the right direction. So if we go with this term, you can see that it is, if you write it out, it's negative 1 A1 negative I direction. And this one, this term is going to be negative P3 A3 in the negative J direction, because the J direction is this way. The S direction is this way. This term and this term become 0. Why? Because we have uniform velocity. So you get no shear forces. Now let's talk about the last two terms. Specifically, this term and this term. Those two terms, write them up down here. Actually equal to the force of the elbow onto the fluid. So they actually equal to negative force of the elbow. So remember, the elbow experiences a reaction force to the fluid, and the fluid experiences a reaction force to the fluid. And how do these forces occur? Through pressure acting on the fluid and shear acting on the fluid, or vice versa. So both of these terms end up being F on the elbow. So if we look to combine our left-hand side and our right-hand side, we end up with rho A1, rho V1 squared times negative A1 I plus A1 squared on A3 J. So this ends up being, that was our left-hand side, and what we do is equate it to our right-hand side. Equals P1 A1 I plus P3 A3 J minus elbow. F. Let me just be a little bit careful. It's probably not going to, we always have to be a little bit careful on how you get this. So instead of calling this F elbow here, what I'm going to do is call it F of elbow on fluid. We'll put a positive sign, F of elbow on fluid. And then we solve for F of elbow on fluid. F of elbow on fluid. So this is the force the elbow is applying to the fluid. It's going to equal rho V1 squared minus A1. Maybe what I could do instead too is start combining these two I terms. So rho V1 squared minus A1 minus rho V1 squared A1 minus P1 A1 the I direction plus rho V1 squared A1 squared on A3 minus P3 A3 J direction. So this yields our force of the elbow on the fluid. And F on the elbow, we simply take a sign. It's going to simply be negative F E on that, or E comma F. So this ends up being what we're looking for. A few notes. Pressure 2 is not satisfied by Bernoulli, but rather the quasi 1D energy equation. You apply Bernoulli here, it's not going to work. You have a head loss where it causes Bernoulli to fail. The other thing is, and this is where a lot of people mess up, is P1 and P3 apply forces to the control volume. Do not forget them. They're critical here. Look at how, just think about this. Pressures on the order of 100,000 pascals and at standard conditions, right? That could lead a lot to the loads applied to this system. So that's it for the example 1, finding the force on an elbow. Next one, we're going to go to an airfoil.